Hey everyone, my name's Louis. I graduated year 12 in 2024, and for specialist mathematics, I got a 49 out of 50 in my EA and a 99 out of 100 overall for specialists. And I'm here today to go through my paper for last year, the paper 1 tech free question and response book. And basically, I'll be going through my thought process so I can hopefully help some of you guys to understand some tips and tricks on how to solve these sorts of problems. Okay, let's go straight into it. So, question 11. I found that this paper in general actually was pretty easy for specialists actually. So, basically what the part A required us to do is we have a vector equation of a straight line given by this formula, and k is a scalar, okay? And we need to express the expression of the line as a pair of parametric equations. So remember, parametric equations is where we have the x equals something and then y equals something, okay? And so in this case, if we think about this equation right here of the straight line, we have x as the top part of the vector. So x is equal to 2 plus k times -1, which we can just say as 2 minus k. Okay, so we write that x equals 2 minus k. And then similarly on the y bottom part, we have y equals 0 plus 2k. So y equals 2k there. Okay, and that is our mark. Right, pretty easy. What I'll quickly do is I'll get the formula sheet up as well on the side here so we can work with it. Okay, yeah, should be coming up now. Cool. And in case you forgot about the vector equation of the line, I believe it's in here. So we have a vector equation of the line, okay, right here. And so that's basically what we're doing. X equals an a value plus a constant, which is k in this case, and a d value, which is the coefficient, okay? And we can also write that obviously in vector form there. Okay, now we have to use our result from question 11a to express the equation of the line as a Cartesian equation. Okay, so pretty simple. We know that y is equal to 2k. So if we just find out what k is from our x equals 2 minus k equation, so we add k to both sides to cancel the negative k out here, and then minus x on both sides, we have 2 minus x equals k, and then we substitute that in, okay, and that will basically be our equation, okay? So you can leave it as that. The marking guide will allow you, since it's only 1 mark, I'll just breeze through these questions, no need to expand, okay? Now, determine the coordinates of the point that the line passes through when k equals 5, okay? I honestly don't know why this was in specialist maths, but basically it's just using this equation, plugging k equals 5, and finding those coordinates, okay? So we have x and y is equal to 2, 0 plus k equals 5, 1, sorry, -1, 2. So these aren't fractions, these are, sorry, I said that. These aren't fractions, these are vectors, okay? So we don't put a horizontal line, okay? And then we simply just add top and bottom. So 2 plus 5 times -1. So 5 times -1 is -5. So 2 minus 5 is -3. And then 0 plus 5 times 2 is 10. Okay. And so you just say, therefore, required point. You would write it in coordinate form. is -3, 10. So that can be a silly way to lose marks. You won't get a mark for just saying the vector. You need to look at the question, it's determine the coordinates of the point. So you need it in coordinate form, okay? So that could have been a trick one as well. It seems simple, but in order to get the marks, you need to be actually giving me coordinates. Okay. And 11D, determine the value of k when the line intersects the y-axis. Okay, well, what we can do, because we have our parametric equations, we know that y equals 2 minus k, okay? And we know that the line intersects the y-axis when, sorry, not y equals 2 minus k, it's x equals 2 minus k, and we would confirm that from what we had up here. Okay, y is equal to 2k, sorry. But basically, at the y-intercept, okay, when it intersects the y-axis, that's the y-intercept, x is equal to 0, okay, because we know at a point, for example, if this was the y-intercept, then x is equal to 0 and y is equal to some value, which is the intercept, okay? And we can just sub x equals 0 into this equation, and 0 equals 2 minus k. We only have k as our unknown, so we can just bring that to the other side. K is equal to 2. Okay, and that is our other mark there. Moving on. Question 12. The point A lies on a section of the ellipse 3x squared plus y squared equals 10 as shown. The coordinates of A are square root of 2 and then y1. So first off, we have to determine the value of y1. Again, this is super easy in specialist math. I mean, even this is tech free, we're working with square roots and squares, so it's not that difficult. But basically, y1 is just going to be the value of y when we plug in square root of 2 for x. Okay, and keeping those equations equal. So 3 times square root of 2 squared plus y1 squared, okay, because we're using our coordinates now where we have x and our y value, equals 10, okay, and then from that we can just simplify. So 3 times square root of 2 squared is just canceling out that square root, plus y1 squared equals 10. We have 6 plus y1 squared equals 10, and then y1 squared equals 4, minusing 6 on both sides, and y1 is going to be the square root plus or minus the square root of 4. Okay, and then y1 is equal to plus or minus 2. All right. However, we know that coordinate A lies in the fourth quadrant. Okay, so if we extend this Cartesian plane, it's the first, second, third quadrant. We know that A lies in the fourth quadrant, but even if you didn't know that, you know that the y value is negative here. It's below the x-axis. Okay, we have a negative value below 0, and so we would have to pick y1 equals -2 given A lies in quadrant 4. Okay, so obviously the reason why this is 2 marks is because we need to evaluate the reasonableness of our solution. Okay, and we also need to give both the plus and minus values because we know when square rooting we always have a plus and minus value, positive and negative value. Okay, so we get 1 mark for simply just substituting into the equation. Okay, that's the first step. All this other stuff is just, it's not specialist math stuff, but we need to know reasonableness of equations and evaluating them. So, you know, given that A lies in the quadrant 4, y1 equals -2 as opposed to +2. That's our second mark, and that gives you full marks there. And now we have to use implicit differentiation. to determine an expression for dy dx in terms of x and y. Okay, so if we just rewrite our original equation so it's easier for us to look back on, then when we do implicit differentiation in terms of x, okay, then 3x squared will be the same. Okay, but however, when differentiating y squared in terms of dy dx, so in terms of x, then we just differentiate it normally how we usually would, but then put a dy dx there, okay, because that's like a chain rule function. And we know deriving 10, which is just a constant, is going to be 0. Okay, and from that, we can just rearrange. All right, so be really confident, guys, with your transposing. Dy dx equals negative 6x over 2y. I can further simplify that. So always put the simplest form, negative 3x over y, because I just divide by 2 both sides. And maybe put there as well that y cannot be equal to 0, because we're giving our boundaries now, because obviously we cannot divide by 0. So if y is on the bottom, then we cannot have y equals 0. So that's 2 marks there. The first mark is using implicit differentiation, which is this one, and the second mark is actually giving the dy dx in terms of x and y. So that's those 2 marks there. Use your results from questions 12a and 12b to determine the gradient of the tangent to the curve at A. Okay. So essentially we have a derivative function now, and that is representative of our gradient. So I'm basically just doing dy dx is when x is equal to square root of 2 and y is equal to negative 2. Okay, so we already have those values from our previous question, so let's use them. Okay, so that's just going to be negative 3 square root of 2 over negative 2. Oh yeah, I had wrote them already here, so I don't know why I looked up, sorry. And then because they're both negatives on top and bottom, I can get rid of that, cancel it both. And that's my gradient. Okay, so that's the 1 mark there, because you only need to show one thing. And then now, consider the region between the given section of the ellipse, the x-axis, and the lines x equals 0 and x equals square root of 2. Okay, so this is quite the most complex one probably for this question. This is basically calculating volume from definite integrals. Okay, so remember our formula. I believe it's here. Here. So we're using this formula. Okay, so I would rewrite that just so I have it with me. Okay, and then I would probably start to note down my a and b values. So a was going to be 0, b is equal to square root of 2 because those are my boundaries. And my f of x function is going to be my y equals something. Okay, so I need to rearrange this equation for the ellipse to make it into y equals something, because then it will be a function of x, where I have x only on the right hand side of my y equation. So y is equal to, so let's try this out ourselves. So 10 minus 3x squared. But however, we will have y squared still, so we have to square root that. So square root there, okay? And so that is our function of x. Okay, however, it doesn't really matter about the square root because we are squaring it anyway. so we can just keep it as is. So v equals pi from integral 0 to square root of 2, 10 minus 3x squared dx. Okay, and then now I'm just basically going to be solving for that. So equals pi, and then remember to differentiate first 10x minus x to the power of 3 there. Okay, so using both methods and specialist knowledge, and then square root of 2, 0. Okay, and then now I'm just substituting in and minusing. So 10 square root of 2 minus square root of 2 to the power of 3. Okay, I'm keeping that in brackets, minus the 10, 0, minus 0 cubed and stuff. So it'll just basically be this part that's left. So pi 10 square root of 2 minus square root of 2 to cubed is going to be, well, I'm going to have a square from the squared, but then I'm having an extra square root 2. Okay, and that gives me 8 square root of 2 left, and therefore volume equals 8 square root of 2 pi units. Okay, and so that is really our mark there, and that's our mark there for determining this definite integral that represents the acquired volume, and then putting the volume in simplest form there. Okay, all right, so question 13. This polynomial of p and q polynomial, and both are in terms of z, where a is a complex number, have the same remainder when divided by z minus I. Use the remainder theorem to determine the value of a. Now we know that when we divide by a complex number such as z minus I, we know that we can find the remainder by substituting in the polynomial that value there in terms of z minus, let's say, c. Right, so when we're dividing a number by dividing by z minus c in terms of our variable that we're using, then we can just substitute in the polynomial the c value, which is negative something. So in this case, z minus I is equal to z minus c. You can notice that I is equal to c, and so we can just substitute that in. So for the first polynomial p, we would substitute I for z, and then we get a times I squared minus I times I plus 1 minus 3I. And then I squared we know is negative 1, so negative a. And then again, I squared is negative 1, so it's going to be negative 1, so plus 1 minus 3I. And that'll be negative a plus 2 minus 3I. Okay, and we can do the same thing for polynomial q. Right, so with q, again, we just substitute in this polynomial equation, wherever the z I put in I, so I squared plus 3I times I plus 2a. And then I know that I squared again is negative 1, and then I squared here is negative 1, so that's going to be negative 3 plus 2a, and that'll be equal to 2a minus 4, just moving the constant on the end there. All right, and because we are using the remainder theorem, and with the given information, that when we divide p and q polynomials by z minus I, then we have the same remainder. Okay, and so therefore, because our equation or formula for finding the remainder for polynomial p and polynomial q is substituting I on both of them, we know that because they have the same remainder, then p of I is equal to q of I, right? So we can just basically equate these two equations now to find A, because we only have A as a variable for those two equations. Okay, so what I would do is I'd probably move the A's on the right hand side because I want to keep my A's positive, so plus A on both sides. You know the drill. 2 minus 3I equals 3A minus 4, and then plus 4 on both sides, so 6 minus 3I equals 3A, and then just dividing 3 on both sides, therefore A is equal to 2 minus I, because I'm dividing by 3 on every term there, okay? And so, just to put that clearly, A is equal to 2 minus I, and I can confirm that. I can confirm that because I know that A is a subset within the complex numbers, and that would be our real component is 2, and our imaginary component is -1. Right. Question 14. The displacement in centimeters of a particle from the origin as it travels in two-dimensional space at time t for 0 to pi over 2 seconds is given by this equation here, right, our displacement equation. Express the path of the particle as a pair of parametric equations. All right, so this is quite similar to what we did in the first question as well. Basically, this is x, this is y. So that, like, it was pretty easy. Again, I don't know why they put this on the specialist math paper, but they did. Okay, it's literally just copying what is in the equation for x and y. All right, and then that's our mark there. Oh, and I'll do the marking scheme again as well for question 13. It was 4 marks, so it's pretty high yield. So you get a mark for correctly using the remainder theorem. So basically just saying where z is equal to I. So probably that's a tick there, but I would probably specifically say z equals I to really save myself for that mark, because we need to show that we're using the remainder theorem, but I guess we also get that mark here using remainder theorem. And then determines the simplified expression for pi, so that's this mark and this mark. So those are the 3 marks, and then the 4th and final mark is determining the value of a. Okay, so that's our 4 marks there. Sorry, and then this one is again full marks there. Part A. Now part B is looking at a general Cartesian form of hyperbola with center h, k, and then it gives us that formula. Okay, and we have to use now a suitable Pythagorean identity to show that the path of the particle can be expressed in this general Cartesian form. Okay, so for this question, I would mention that I'd probably look back to A and then I would label my different equations. Sorry. So this would be equation 1, and then this would be equation 2. Okay, just so I can pass that on into this part B equation, right? So from 1, we can basically transpose this first equation to get sec t on its own. So sec t, well, if we plus 1 on both sides and divide by 2 on everything, that would be x plus 1 over 2. Okay, and then now we have to use a Pythagorean identity. So I'll say using the Pythagorean identity, which is tan squared a plus 1 equals sec squared a. And again, I can check that it's on my formula sheet. So it'd be on trigonometry, I believe. That is it. Tan squared, this one. Yep, so Pythagorean identities. We have 3 to choose from. We just choose the one with the sec because that's what we have there for the x part of the equation. Okay. And then from that, I can now say that from equation 2, and if we make this top equation up here 3, then I know that my tan squared of a is just essentially y squared because, well, if we let a equals t, which would be the angle in this case, or seconds, then I'm basically just doing y squared, which is tan squared of t, plus 1. Again, I'm just doing this exactly how it is in the formula. And then equals, I know that sec squared a is going to be just the square of the sec t. Well, in this case, it would be t. So the angle is t. So if I know that sec t up here is just x plus 1 all over 2, then sec squared t is going to be the square of that right hand side. Okay, and then now from that I can bring it back to this general Cartesian form because I need to show that the path of the particle can be expressed in the general Cartesian form. So I need to show it in this form here. So I need to have equals 1 on the right hand side. So I can do that just easily swapping the left and right hand side, but I need to minus y squared on both sides to get rid of this hanging y squared on together with the 1 on that side. So that would give me x plus 1 over I might get just the square on the top part of the fraction, so x plus 1 squared, and then I would just square my denominator. So I know that that can simplify to a 4 on the bottom because 2 squared is 4. And then I'm minusing y squared, and that will equal to 1. Okay, and that's basically it. Like, those are the 3 marks I get. So the first mark is by expressing sec t as the subject of the formula. So having that on the one side of the formula, and then using the suitable Pythagorean identity, so rewriting that equation, and then having our final step as expressing that as the path of the particle in the general Cartesian form. You can see that h in this case would be -1, okay, and then a is 2, because that's being square on the bottom, and then obviously k would be 0 in this case because there's no translation. It's just going to be simply y squared, and then b is just 1. And that follows the limits as well, where a and b cannot equal to 0. And last part, determining the center of the hyperbolic path of the particle. Very easy for 1 mark. It's basically just h comma k, all right, because it just says in the question already that's the center. And therefore, if I know my general equation has a minus k and I have a plus, minus h, and then my actual equation has a plus h, which is +1, then I know that it's actually going to be -1 when I substitute that. And then k will obviously be 0. We've mentioned that. So that's that mark there. And that's full marks for question 14. All right, question 15 was on slope fields. And so the question says, a sketch of a partially completed slope field for the differential equation dy dx equals 1 minus y is shown. And then we have to complete the slope field by sketching the slopes at the 10 points I indicated, which are obviously that 5×2 points right here in the top. And so there's really only 2 marks because there are 2 different types of slopes you can do. Again, this was a pretty easy paper, I'd say. So we know that when y is equal to 1, then our dy dx, or our slope, or gradient, is going to be 1 minus 1, 0. Okay, very easy tech freestyle paper. And then again, if y is equal to 2, then I'm just changing that to 1 minus 2, and that's going to give me -1 slope. So that'll give me around a 45-degree angle. So I guess remembering our tan of -1 to give us the angle. And I think that would be a negative out the front of the tan, so that'll be -45 degrees Celsius. Sorry, just degrees, not Celsius. And that would be a downward slope. So maybe like just those slopes here, okay? But basically, it's easy, free marks here. 1 mark for the slope as 0 for y equals 1, and the slope as -1 for y equals 2. All right, moving on. Use the completed slope field to sketch the solution curve for dy dx equals 1 minus y, given the point -1, 0 lies on this curve. Okay, so what we can do is put the point -1, 0 on our graph, and then think about how the line moves as we go through. So we know that there's going to be essentially a slope going this way in that angle, so that's the gradient at that point, but then it sort of plateaus at y equals 1, so we start getting a straight horizontal plateau there, and then again here we get more steeper going down. Okay, so that's really all you have to do. Maybe label -1, 0 to be really sure about that the line passes through there, but other than that, I think you just get the mark. Really, it says in the marking scheme to sketch a solution curve that passes through -1, 0 and is asymptomatic to the line y equals 1. Y equals 1 is our asymptote, horizontal asymptote. Okay. So it doesn't really actually require us to give that equation. Yeah. However, you may need to use it in part C. Okay. So that's that mark there. And then part C is 3 marks. The differential equation can be solved by rearranging it into the form 1 over 1 minus y dy dx equals 1. Okay. And that makes sense because we're essentially just dividing both sides by 1 minus y. So now we have to determine the equation of the solution curve sketched in question 15b. Yes, so this is now trying to find what that equation curve actually was. Okay, so it looks to me it would be a probably like a exponential / logarithmic, depends on what we get as well. So that's can be a quick dummy check to see what type of equation we need to work with. All right, and then what we can do now is we can rearrange our dy and dx on separate sides. So if we just rewrite that form, there's 2 methods to solve this. So I'll give both methods as are in my working out. So this is method 1. This is probably how I would have done it as well. Okay, so again, just rewriting this thing in yellow that I've highlighted. And so we have 1 over 1 minus y dy dx equals 1. And then I want to integrate both sides, but first I need to bring our dx to the other side. So like that. Okay. And then I know that if I'm integrating a fraction like this and my variable's in the bottom, then that -1 coefficient on the y becomes my outside, I guess, part of the integral, negative, and then it's always going to be ln, and then just that bottom part, the denominator, in absolute value sign, is equal to integral of 1 is easy, x plus c. Okay, and I know that at my point, -1, 0, then I can just substitute that to find c. So negative ln 1 minus 0 equals -1 plus c. That's negative ln of 1 is equal to -1 plus c. Ln of 1, anything where we have a log with the number in the bracket is 1 is just going to be 0. And that means that c is equal to 1, positive 1. Okay? And then now I can just substitute that back into my original equation that I had up here. I believe. However, I'm going to remove that negative part in front of the ln just so I can have a nice, neat change for my conversion to an exponential form where I just have y on one side of the equation. So I would make sure I have negative x and then -1. So I'm negating both sides. I need to negate every term. Okay, and then again, if you remember, our conversion from logarithmic to exponential form, if I have a base E here, then I'm basically just doing anti-clockwise rotation. So e to the power of negative x minus 1 equals, and then going again anti-clockwise, this is what's going to be on my other side of the equation, 1 minus y. And then I want to get y on its own positively on one side, so I'm going to bring it to the left hand side, so plus y on both sides, and then minus this entire thing as well. The negative, I'm going to minus e to the power of negative x minus 1 on both sides. Okay, and that's my solution. Okay, so the 3 marks there, the first mark in this first method at least, is to correctly determine a general solution to the equation, which is this part here, and then find that c value, and then the final mark is this one. Okay. Now method 2. So personally, I would do method 1. In my exam, I'm pretty sure that's what I did anyway. Method 2, I'm just going to look and explain through what's on the marking guide so that you have other options as well. Okay, so essentially it's similar steps. Okay, so I won't repeat my explanation for those. I'll just explain what's the difference. Okay, so notice that mark is still the same, so you have to do that either way, finding the general solution of the equation. And then what I can also do now is I can go straight to my logarithmic form and say, well, my 1 minus y is equal to e to the, again, I'm taking this negative away on both sides, so I need to negate both sides. Okay, doing that, and then therefore y is equal to 1 minus the e to the negative x minus c. So for similar reasons what we did here as well, except I think we're just doing this at an earlier step as like our second step of the equation. And what, so oh yes, so I believe actually the main difference is because we have our constant, we're trying to find that constant. Remember that we can separate these exponents using our exponent laws, index laws, and e to the, I believe e to the negative x minus c is equal to e to the negative x over e to the c. Okay, and my e to the c is can just be put, I can just make my 1 over e to the c as a value, I might say a. Okay, so I'll do y equals 1 minus a e to the power of negative x. So that removes that negative c part, and I can just find what a is and then equate those two. So I know that at negative 1, 0, that I can just substitute those x and y values. 0 equals 1 minus a times e to the power of negative 1, which is just going to give me a e equals 1, a is equal to 1 over e. Okay, and obviously my c value was just gonna be 1 as well, so that works out. And then I can just substitute my a value back into this equation here and then say therefore y is equal to 1 minus 1 over e times e to the power of negative x. Okay, so those two equations are actually equivalent, these two equations at the bottom that I've put in boxes. Okay, and if you think about it, it's because we can separate the e to the minus x minus 1 into e to the minus x over e to the 1, because I'm using my index laws to know that this subtraction between those two different terms on the power are a result of my index laws for dividing two numbers which have the same base but different powers. Okay, and so that I'm just taking this e on the bottom and making that into putting that in the front to say that's equal to 1 over e times e to the negative x. Okay, another form you could say is again like just this form up here where you just plug this up here, but the exam marking sheet just gives this in the boxes. So choose your method. I would definitely go with method 1. It's much more simpler, and I know that my c is always going to be my constant of integration. Question 16. So we're now getting to the complex familiar questions. And we know that there are two complex familiar questions, 16 and 17, and then 18 and 19 are my complex unfamiliar questions. So that's typically what it's going to look like in general. There may be some slight variations though. Alright, so for this question, there are actually 3 different methods that have been provided. I won't do all of them just to save time. I'll have a look and see ahead which method that I prefer to use and what I did during my exam. Okay. What I might do is I'll do it myself first and just making sure that I'm on the right track. So remember, our first mark is by correctly proving the initial statement. So we say let n equals 1. Alright, so these mathematical induction questions, they're easy marks because, you know, even though there's 6 marks, you get the same marks for basically every single thing, and it doesn't really change at all. And it comes out pretty nicely as well because we need to prove something. We already know that it's going to be a multiple of 7, so we need to make sure that our numbers match and everything. So there's really no reason that we can lose marks or you know, get anything below 6 marks for this question. All right, so again, if I'm letting n equals 1, what am I doing? I'm just literally substituting wherever there's n in my proof equation thing, then I am putting a 1 there. So all right, and then again I'm looking ahead and seeing, oh, this is a multiple question. All right, so this is asking about like equating two things. This is about multiples, so I know I need to use like a 7m somewhere in my working out as well. Okay, so now I'm just looking ahead. All right, so in this case, 12 plus 2 times 5 to the power of 1 minus 1, well, this power will be 0. 5 to the power of 0 is 1, so 12 plus 2 is just 14, okay, which is 7 times 2. Remember, you need to put 7 times 2 because it shows that the n equals 1, like this part when n equals 1, is a factor or a multiple. Sorry, not a factor. It's a multiple of 7. Okay, because this shows if I write 14, that doesn't prove anything to me. I need to clearly indicate that 14 is a multiple of 7 because I can do 7 times 2. So 2 multiples of 7. And those are whole multiples as well. Okay, and then I would say therefore true for n equals 1. Okay, that is my first mark. All right, it's the same for every question you'll get on mathematical induction. The second mark is by correctly formulating an appropriate assumption. So now we say assume true for n equals k. All right, so in this case, everywhere there's n, just put a k. And then for multiple questions, multiple type questions, I just use the letter m, lowercase m, and then I have to give a range for that number as well. So 7m is like my version of saying 7, a multiple of 7, where m is a subset of basically positive integers. Okay, and that's the symbol for that. Okay, and then I can say that's my equation 1. Now, my inductive step is saying let n equals k plus 1. Okay, so now I have the 12 to the power of k plus 1. So again, I'm just substituting n's. And sorry, the second mark is making that assumption. The third mark is by, well, I'll get to the third mark, is by basically doing the n equals k plus 1 substitution. Okay, so it's really that easy. And we'll obviously have to simplify it to get the mark. 5 to the power k. Yeah, so that's my third mark. All right, so these are easy marks. These are things that that anyone can do, honestly. All right, so just to recap. Let n equals 1. Assume true for n equals k and let n equals k plus 1. Okay, it's a step-by-step process. They'll give you already half the marks. Okay, so that is the third mark, where we correctly establish an appropriate expression representing the left-hand side of the inductive step. Okay, now this is a special step that I personally do. It's not on the marking scheme. I just checked and I've been editing this video. But a trick I like to show you is that when I do the assumption step, I'll also add something where I basically get 12 to the k. So usually there'll be just a single number to the power of something, and that's quite simple to work with. But I'm just going to do 7m minus the something, which is this complex thing right here with the k minus 1 typically. So 2 times 5 to the k minus 1. And that'll be useful when I go down and use my induction step here. So remember, I'm equating all these equations here, right? And I want to prove that this part of the induction sort of step, where n equals k plus 1, is also a multiple of 7, and that completes my proof. But I need to use the assumption that I made in equation 1 here, right? So I need to use my index laws, knowing that 12 to the power of k plus 1 can be split into 12 to the power of 1 and 12 to the power of k, because multiplying two numbers with the same base but different powers are just adding those powers, so k plus 1. But now that I have a 12 to the k on its own, I can substitute that into here and then see what I'm working with. Okay? And the reason I'm doing this is because I can work with numbers that have like terms, and hopefully I get a number. All the numbers that I get as coefficients for those like terms are going to be multiples of 7 that I can then factorize out. So basically factorizing 7 out of each term and then proving it it is a multiple. Okay, so I would put 12 to the power of 1, which is just 12, times 7m minus 2 times 5 to the k minus 1 plus 2 to the 5 k. Yeah. So I wouldn't worry too much at the moment about why there's only just the 5 to the k. Those aren't like terms, but I can do a k minus 1 sneakily and then add multiply by 5 to sort of balance it out again. So canceling it out. It's like doing it backwards this time. It's like um, I want a 5 to the k minus 1, but in order to do that, I need to sort of undo that step, but in a different way. So that means my 2 and 5 here can become 2 times 5, which is 10 lots of the 5k minus 1. So I'm going to also expand out this side for the brackets. So 84m minus 24 5k minus 1. So notice my 24, a coefficient in front of the 5k minus 1 is not a factor of 7. However, once I do 2 times 5, which is 10, positive 10, times 5 to the k minus 1, then I have basically like terms now. So these green underlines, they are like terms because they're just basically lots of the 5 to the power of k minus 1. Negative 24 lots plus 10 lots of that I've highlighted in yellow. And so I have 84m minus 14 times 5 to the k minus 1. Okay? And now I can clearly see that I can factorize a 7 out of all this. 7 times 12m, sorry, minus 2 times 5 to the k minus 1. And that's going to be equal to 7q, where q is obviously going to be a positive integer because my k is obviously the same subset of n, which is a positive integer, as well as my m. I have stated in my assumption that m is a positive integer as well here. Then therefore, as true for n equals 1, n equals k, and n equals k plus 1, then true for I'd say for all n is a subset of, and from my question I just copy it, positive integers. Okay, and this symbol here is for all, which is like a fancy term to use, fancy symbol to use in maths. Right. So the half of the marks, so my 4th, 5th, and 6th mark, respectively, would come from uses the assumption. So basically substituting equation 1 into my inductive step, which would be this step right here. So that's a tick. The 5th mark is by completing my proof here by showing that it is indeed a multiple of 7. And then my 6th and final step is obviously showing that logical organization, having attempted all steps of the proof, including a suitable conclusion. So you must always do a conclusion. And it is literally always the same. Doesn't change. I say, therefore, it's a symbol, as true for n equals 1, n equals k, and n equals k plus 1, which is my 1st, 2nd, and 3rd mark. Then this is my other half of the marks, true for all n is a subset of z positive integers, and that is literally just copying from the question. So I always copy the question on what I guess domain sort of range subset they want you to use. Okay, cool. All right. Question 17. The acceleration in meters per second squared of an object that moves in a straight line in an easterly direction over time, t, for 0 to pi over 6 seconds is given by this formula here, where v is its velocity, okay? The object is initially at rest at a position that is ln square root of 2 meters west of the origin, and Eschewing uses this information to calculate the object is positioned at the origin when t equals pi over 6 seconds. Evaluate the reasonableness of the Eschewing's calculation. Okay. So let's write some facts that we know. We know that the acceleration equation is this here. Okay. And I know that my acceleration is actually just deriving my velocity in terms of time. And now I can start to integrate and rearrange. So I can divide 1 plus v squared on both sides. So I can bring my v's together. So and integrate both sides as well. So integral of 1 over 1 plus v squared dv is equal to the integral of 2 in terms of t. And then I know that my integral of anything where it's 1 over 1 plus my variable squared. I check my formula sheet for integrals. That's simply going to be my tan to the negative 1, inverse tan. Okay, so that fits in quite nicely. So that's going to be tan inverse v equals 2t plus c. Okay, and I can find out what c is because I know that at time equals 0, then the object is initially at rest. My velocity is equal to 0 as well. So I can use that knowledge to say that the inverse tan of my velocity, which is 0, is equal to 2 times 0, which is 0, plus c. So c is equal to 0 because I know my tan inverse is 0 of 0 is 0 because if we know that tan is just sine over cos, and in order to get 0, I just need to have as the top as 0, which is sine, and yeah, I know that just common knowledge that the inverse tan is 0. I think knowing your exact values for inverse tans and sines and cos are pretty important as well. Don't really have much of an explanation for that, but as long as you know that, it should be all good. Or you could draw a diagram as well. But yeah, if you think about it, doing tan of 0 will get you 0, and so inverse tan is the same thing. That's how I like to remember it, I think. Okay, so therefore c is equal to 0 there. So therefore, I know that tan inverse of v is equal to just the 2t. Okay? And what I can do now is Um, I understand that x, sorry, I might do just, I will tan both sides of the equation. So v is equal to, obviously, tanning a inverse tan is just canceling it out. So tan is, yeah, v is equal to tan 2t, okay? And then I can get my displacement equation, which is x is equal to an integral of v in terms of in terms of t, time, and that's going to be integral of tan 2t dt. All right, and I know that tan is sine over cos, as I mentioned. Okay, and this is really just the hard part, but basically, do I have an integral for tan? Integral. No, I don't have an integral for tan. Okay. Well, I think this. Um, okay. So I think the solution here is thinking about when we have integrating of fractions, we usually have ln, right? So if we differentiate just the bottom part of the denominator, so let's say we differentiate that, right? We get -2 sine 2t. Okay, so if I just basically manipulate the numerator now to have the -2 at the front, I need to still keep everything balanced. So because I have an equation symbol, I need to keep everything balanced. So to cancel it out on the other side, outside the integral, I have a -1/2. Okay, because that will just keep everything equivalent. Like I haven't changed anything in the equation, I've just changed how it looks, essentially. Okay, and now that works because once I do an integral of this fraction right here, I might highlight it in yellow, this fraction right here, then I know that essentially what I'm doing is I'm taking the derivative of the bottom part of the fraction, so the denominator, and then I'm dividing that by the numerator, or sort of the whole fraction in total. Okay, so x is going to be equal to -1/2 ln, and then I just have that cos function in my absolute symbols plus c. Okay. Um, if that's difficult to understand, then maybe try differentiating it again. So doing it the backwards way, and then seeing how, if we differentiate, just say this yellow part, then I'm going to get the basically differentiating cos 2t, which is -2 sine 2t, and then because it's an ln function, I'm going to have what's in the absolute signs in between them is going to be in my denominator. Okay, so that's basically equivalent to there. I'm not too sure if that helps, but that is one method to go about it and thinking about it there. Cool. And then from that, I have that general solution for displacement, and I can figure out my C value, okay? So given that x is equal to negative ln square root of 2 when t equals 0, because I know that the object is initially, so t equals 0 means initially position is ln square root 2, but it's west of the origin because I know that the acceleration is positive when I'm moving in a straight line in an easterly direction. So I need to use negative values. Okay, so that's the complex part of this question, essentially. We need to have a negative ln square root of 2. Okay, and then now I have x is equal to negative half ln cos 2t. Apologies there, I meant to substitute x is equal to negative ln square root of 2, and then t is 0, so I'm making that 2 times 0 here. Let's see, because I'm trying to find my c value. So negative ln square root of 2 is equal to negative half. I know cos of 0 is just 1, so ln of 1 is just going to be 0, so that's going to be 0 on that side, plus c. And I know that when I'm taking a negative, c can just be negative ln square root of 2. Okay, that'll give me the marks anyway. And then now I can just rewrite the displacement. Okay. Now, when t is pi over 6, which is now we're trying to evaluate the reasonableness of the student's calculation because we have the object's position as an equation. We need to substitute t equals pi over 6 and have a look and see if x equals equal to 0, and then use that to determine whether the calculation is reasonable. So x is equal to 0 actually, or if it's not reasonable. So when t is equal to pi over 6, and remember this is a tech-free paper, so all the calculations should be fairly simple. X equals negative half ln cos 2 times pi over 6 is pi over 3 minus ln square root of 2. Okay, I know that cos pi over 3 is a half. Okay, minus ln square root of 2. And then now I have, what can I do? I can move this negative half out the front and say this is ln a half to the power of negative a half minus ln square root of 2. And I know that if I have a negative in the power from my ln, then I can actually just swap that, and it becomes a positive now, minus ln square root of 2. And I know that raising a number to the power of half is just going to square root in that bracket. And that will give me cancelled out 0. And I'd say therefore the calculation is reasonable. So just summarizing and finishing up on this question, it's 6 marks again. And so the first mark is correctly determining a general solution to the differential equation in terms of v and time, which is this one right here. And then now we have to find our c value. Second mark, general equation for the displacement in terms of time, this one, and then find the C value, that one, and then now determines the result for when t is equals pi over 6 is this one, and then calculation is reasonable. It's providing a statement for the reasonableness. Okay, so that's R for 6 marks there. Easy. All right, so moving on to our complex unfamiliar questions. Question 18 for 6 marks. We have a random variable x having the probability density function, or PDF, given by this right here, okay, where k is a positive constant, and we need to determine the value of k, right? So firstly, the first mark comes from correctly using a suitable PDF property. So we know that for probability density functions, if we remember our graph here, we would have our peak there, and then so that's sort of like a normal distribution. It could be a normal distribution, but essentially we know that with PDF function, PDFs, probability density functions, that the area underneath the curve from 0 to 1, so from 0 to 1 on the x-axis, is going to equal to 0, okay? So using a property of a PDF, we know that the integral, or area, from 0 to 1 for this PDF function in terms of x is equal to 1. And that's going to be my first equation. All right. And now we have to look at this and see, okay, we need to figure out a method to integrate this function. So we can see that if we just take a indefinite integral of that PDF function in terms of x, and we consider that, we can use integration by parts. And I know that because I have two distinct parts. So I have a k aspect constant as well as a sine inverse component to it. All right. And obviously, I would want my simplest component to be my differential because it's easier to, I guess, integrate then. So that means my dv dx is going to equal k. So my v is going to be the integral, the integral of k, which is kx, because we're integrating in terms of x, or dx. And then my u is going to be that sine inverse function. And then if I derive that, then I look in my formula sheet, differentiating and inverse sine gives me one over the square root of a squared minus x squared. Okay, and my a value in this case is just 1, because I'm dividing by 1 inside the brackets, because it's just x over there. So that would be x over 1 there. Okay, and then obviously my x value, I don't have a coefficient there, so it's simply just going to be 1 there. So my du dx is 1 over square root of 1, which is my a value, minus x squared there. Right, so that matches my formula sheet for calculus there. This one. Cool. Right. So the second mark comes from correctly determining both results required to progress integration by parts. So that's this one and this one, right? And then I need to use my formula for integration of parts, which is integral of u dv dx in terms of dx is equal to u times v minus integral of v du dx in terms of x, okay? And I know that this format here on the left-hand side of the equation follows this format here, excluding the 0 and 1, of course, boundaries, because we're taking an indefinite integral. We have a u value, which is our sine to the negative inverse sine x, and our dv dx value, which is just k. And if I multiply those together and then integrate that, then I'm using my integration of parts formula, right? So that's my application of it. And then obviously I would now just substitute what these actually are. So I know my u is the sine inverse and my dv dx is my k. So again, same thing, but now I'm just integrating by parts. So I'm actually using my uv and v du dx. So u times v is going to be kx sine inverse times x minus the integral of v times du dx. So that would be kx over 1 square root of 1 minus x squared dx. Okay. And then now what I can do is I can look at my integral function, the second one I have, and see what I can maybe work with. So I have a kx on the numerator and then a x squared on the denominator. I know it's square root, but we can still work with that if we use substitution for this integral. So let's consider the integral kx over the square root of 1 minus x squared in terms of x. I can let u on the bottom be 1 minus x squared, okay? And then if I differentiate that, then I get obviously minus 2x. And once I've figured out my du dx is equal to negative 2x, then I can rearrange this by swapping the dx and the negative 2x to form du over negative 2x is equal to dx. And I can easily substitute this dx here and then replace it with that, okay? So I'll show you what that looks like. Okay, so basically what we're doing is, well, we want our du dx, the negative 2x, to be on the numerator. So I'm going to keep the denominator the same for my integral, all right? And then put a negative 2x here, all right? Keeping it still in terms of dx. But because I have a negative 2x, I don't want to simply just change the left and right hand side. I need to keep them equal. So I still need to have a k at the top. I need to keep it negative overall because on the left hand side I have a positive value for the integral. So negative negative cancels out. And then I need to divide by 2 on the outside so I can cancel out these 2's on the top and bottom. Okay, because I don't have any 2's on my left hand side. So I need to cancel it out basically. And then from that, I can start substituting my values in for u and also my dx. So I can do negative k over 2 integral of, well, I know in the denominator that's going to be the square root of u because I let u equal 1 minus x squared. And then with the negative 2x and my dx being now du over negative 2x, then I can now, the benefit of making the numerator negative 2x, which was my du dx, is now I can easily and very beautifully cancel these two out, top and bottom, and then I'm left with just simply, I'll make it as a new line actually. I'm left with negative k over 2 square integral of 1 over square root of u du. Okay, and now I can easily work with this. This is simply methods integral now, so equal to negative k over 2 the integral of u to the power of negative a half, because a half is my square root, but a negative means that it's at the denominator or the bottom of this fraction. Integrating that with respect to u, okay, and I know that that's going to give me, well, if I add 1 to the power and then divide that by what I've added, then I'm going to be having a half on the bottom, so I'm going to be timesing by 2 essentially, 2u and to the power of negative half plus 1, which is a half. Okay, and because my 2's on the bottom and top easily cancel out, so I know I'm on the right track because this is a tech-free paper and they'll only expect me to be doing pretty simple maths here in terms of my arithmetic, which is great. And then remember, my u is actually something with terms of x, so I need to substitute that back in. So negative k times the square root of 1 minus x squared plus c is my indefinite integral there for this entire thing, the integral of kx over square root of 1 minus x squared. Okay, and now I know that my integral of the entire PDF, because remember, go back to our roots, what we were trying to do originally is that the integral of k inverse sine x dx is equal to now kx. So going back up here, basically this line here, right? So kx inverse sine of x plus, and now I put in this value here. But because remember, I initially had a minus at the front here because uv minus my integral. So if my entire integral is negative and I'm minusing the integral, then I'm overall making a positive. So that's a key thing as well, not to forget. So plus k times the square root of 1 minus x squared, so just basically what's in our top line, and then our plus c value. And then to figure out what the c value is, I can, actually I don't need to find my c value, it's not important to me because I'm taking a definite integral actually from 0 to 1. So because obviously my c's will cancel out when I do a definite integral. So I can substitute this now into equation 1. Where I had the integral of basically that PDF function. So I've just written down from 0 to 1 for x, and that equals a total area of 1 unit, okay, squared. And so basically I'll just rewrite it so it's clear. Dx, we're working in terms of x, yeah, is equal to 1. And then I know that if I just do the integral now, I can actually take a common factor. So I'll just be working out with this part right here because I won't be working with my c's. I can see any common factors I can take out. I can take out a k. And that might be really important because I'm trying to find k, remember? So you always try and find common factors when you're taking a definite integral and putting that into our square brackets. So and then obviously just factor out. So decays, so x sine inverse x plus square root of 1 minus x squared, and that's from the boundaries from 0 to 1. That's going to equal to a total value of 1 area unit squared. Okay, and now what I can do is I can simply just substitute 1 for x and then minus everything but 0 is subbed in for x. So 1 sine inverse of 1 plus the square root of 1 minus 1 squared minus 0 inverse sine of 0 plus square root of 1 minus 0 squared. Okay, and then that equals to 1. Right, so and then my sine inverse of 1, if I think about that for a sec, that's going to be, I think, check my unit circle, and my sine value is always the y, and my cos value is the x. Then if I want my sine to equal 1, then the angle I'm making is 90 degrees, and so that's my inverse there, and that'll just be pi over 2. For working in radians, because I think we wanted a form, yeah, we'll just work with radians here because I think it's easier rather than saying 90 degrees, and it's more, I guess, mathematically what we're working with. 1 minus 1 squared is 0, so that'll just cancel out neatly. And then I'm doing minus 0 times anything is going to be 0, but my plus a square root of 1 minus 0 squared, that's going to be square root of 1, which is 1. Okay, that's equal to 1 total area. And then now I can easily just do my fractions, so make these two fractions have the same denominator. So pi over 2, I'm going to times 2 on the top and bottom for my second fraction. And then I'll combine those fractions together with a common denominator. And then now I'm essentially just flipping or making the reciprocal equal to that k, because I'm now just timesing 2 over pi over 2 on both sides to cancel out the top and bottom on the left hand side. And then I'm simply, because I'm just timesing by 1, it'll just be the same thing. Okay, so k is equal to 2 over pi minus 2, and that is my answer. So I've lost track a bit on what marks we have to get, but the third mark came from using that integration of two parts, so getting this formula right here in this step. And then my fourth mark is from using a suitable substitution method, so that's using my let u equals 1 minus x squared and then substituting it into here as well. That constitutes 1 mark, and then determining a general result for the required integral, which is this part with the plus c. Yes, this part right here with the plus c. And then obviously the last 6 mark is by finding the value of k. And that's my 6 marks there. Sweet. Now on to the last question. Question 19. Okay. So we need to consider the complex numbers of the form w equals x plus I, where x is a positive real number. Obviously the I is our imaginary component. And if the real value of w to the power of 7 is equal to 0, then we need to determine all possible values of x. Okay, so the method I would use for this one would probably be De Moivre's theorem. It's in the formula and it's quite simple to use there. although there's obviously many methods to go about complex unfamiliar questions, I'll just do what I thought of during my exam. So, I would write down what I know again just to keep my mind fresh and actually try and understand what this question is asking for me. And then I would let W now be in my cis form, so R cis theta. Okay, so again, that's in my formula sheet, I believe. Let's check that. Yeah, so that's now going to be in my form of R cis theta. And I can apply De Moivre's theorem because I'm raising it to a power, which is 7, and that's quite a big power, so I don't want to have to do, I guess, raising it to the power of 7 and showing all my working out and doing it manually. Okay, I want to be using a quicker shortcut method, which is De Moivre's theorem, and show my working out in specialist maths thinking. All right, and so I know that W to the power of 7 is equal to R to the power of 7, because I'm now just raising that power of the magnitude, but I have to times my angle together. Okay, so that's our first mark. Now notice with these complex unfamiliar questions, even if you feel like this is like, whoa, this is completely like something I don't know about, you can still get marks and do pretty well on these questions just by showing your specialist knowledge that relates to this question. Okay, because that is literally just De Moivre's theorem and it's on the formula sheet, so there's no reason why you can't get that mark. So never leave these questions blank, and just always think about what simple familiar concepts can you take and demonstrate within the complex unfamiliar questions. And that's probably the best way to get started as well with these sort of questions. So, I raise my magnitude, which is lowercase r here, to that power that I'm raising it by, and then I'm timesing that power that I'm raising the entire complex number, and I'm multiplying it by the angle inside my cis, which is my cos angle, which is theta, plus my imaginary I sine theta. So we know that cis is equal to cos, or cis of theta is cos theta plus I sine of theta. Okay, it's just the short form. And now I want to think now about my argument, which is obviously my angle within my W form is equal to theta. Okay, argument's another way to talk about angles in complex numbers. It could be in your formula sheet. I'll just double check. Yeah, it's in there. Okay, so just simply, writing down that argument formula and then taking this form now with the tan theta, but then instead of y and x, it would obviously be so what do we have? We have tan theta equal y over x. So I'll just write that down quickly. So my tan of theta is actually y over x, which would relate to my imaginary coefficient component, and my x is my real. Okay, and I know then that if we want to find what theta is, because I guess that's sort of the first step in order to find the possible values for x. I need to start thinking about De Moivre's theorem, and I can work with angles. Then inverse of tan for y, which in this case would be 1, because I only have 1 times the imaginary component, so that fraction would be 1 over, and then x, well, I just have the 1 there, so that would just be my x there. Okay. and obviously x cannot be 0. So I might give my domains there, and x has to be a real number that's positive because that's given in the question as well. So given that my real component, when I raise my w complex number to the power of 7 is equal to 0, then my argument for that complex number raised to the power of 7 is equal to, and this requires a bit of forward thinking, but if you imagine like the unit circle, right? My real component, which is the cos, and my imaginary opponent, which is the sine, which is, again, our x, cos, imaginary, sine, it's y. If my real component is 0, then I need to be making sure that my values lie along the imaginary line, or like the y-axis, essentially, okay? Because when I'm on the y-axis, then x, or the real component, is equal to 0, all right? And I know that my angles, so this angle would right here, if we go a 90-degree angle, or pi over 2, that's the first time from, let's say, the angle of 0 degrees, in an anti-clockwise motion. That's the first time. Pi over 2 is the first time that I reach a real component where it's equal to 0, okay? So my key part is going to be pi over 2. However, I need to remember that because I have raised my power to 7, there are technically, I guess, I can also be down here as well, and then I can be up here again, and up here and down here. So I need to consider all the possible values. There would be around like maybe 7 of them because I'm raising it to the power of 7. And eventually I know that I will be actually dividing by 7 for the angles and getting my possible values for x essentially from there. Okay. So I need to use the formula pi over 2 2n plus 1 times pi over 2. Okay. Now you may be wondering, what on earth does that mean? Well, it's a way of basically, instead of typically what people do is they do pi over 2, 3 pi over 2, 5 pi over 2, or maybe, I don't know, they do like negative pi over 2 to show on the unit circle. I'll just rewrite again these different points. So maybe this point is pi over 2, but then this point is 3 pi over 2, or negative pi over 2. And then when they go back again, that's another 2 pi and a half. So that's 5 over 2. And like you can do that method with the commas, but I like to keep it into a formula where basically n is a integer. So whether that's positive, negative, that doesn't really matter. But as long as I have a range of values and I can work with that, then that should be good for me, because my pi over 2, that's like my sort of base point. And then I can have multiple different angles that still satisfy this component where the real value, a real component for this w to the power of 7 is equal to 0. Okay? Basically multiple points on the y-axis. When I keep going around my unit circle and make maybe like 3 or 4 revolutions, there are different angles I can make and different forms I can write as that angle. So for example, if n is equal to 0, let's substitute that in. quickly. 2 times 0 plus 1, that's 1, times half over 2, sorry, pi over 2, that's going to be pi over 2 as an angle. If I have n equals 1, then that's going to equal 2 times 1 plus 1 is 3, 3 pi over 2. That's also another angle that I can use for my argument. It still satisfies the equation. What about n equals, I don't know, n equals 2, okay? 2 times 2 is 4, plus 1 is 5, 5 pi on 2. That also satisfies that, okay? Cool. All right. So now I can sort of work with this formula now where I have basically my argument for w to the power of 7 is just going to be 7 times that tan that I was talking about, inverse tan 1 over x. Because I know that my argument my argument for w to the power of 7 is going to be 7 theta, because I talked about how that's De Morbius theorem essentially, and my theta value again is up here. I said that was going to be the inverse tan of 1 over x, so I'm just basically substituting that here now. Okay, and that's equal to 2n plus 1 times pi over 2. Okay, and then I can now, I guess, divide 7 on both sides, so tan inverse of 1 over x equals the 2n plus 1 up pi. Now put that in the numerator together over 14. And my goal now is really to just try and get x on one side of the equation, because that's my goal. Remember, I need to determine all the possible values of x. So the first way to do that is to actually get x on its own on one side of the equation. So the opposite of tan inverse is just tanning. So tan of both sides, we'll cancel that out. Okay, so 1 over x, so that's what's in the bracket, is equal to tan 2n plus 1 times pi over 14. Okay, and I know that if I just take the inverse of, well, not the inverse, but the reciprocal of tan, so I do 1 over tan, that will get me a cot value. Okay, I don't know if this is in the formula sheet, but I might check. Now, that also requires you to understand what cot means. Let's see if they put in cot. Wasn't too sure. Yeah, it doesn't seem like there's any cot. However, yeah, I guess it's just a thing you learn, and with practice with these sort of questions, you'll understand that if you do 1 over tan, that is equal to cot. 1 over sine is equal to 1 is basically cosec. Sine of x, cosec x, and 1 over cos x is sec x, I believe. Okay, and I think with the sec x, that came with our formulas before about Pythagorean identities. Yeah, cot is there. So yeah, sorry. So now that I know that cot's there, then I can think about, well, if I did Um, just, um, yeah, I'm not too got. Yeah, there's something with the when we derive this equation that allows us to understand what cot means, but I'm not too confident and sure about that one right now. But I mean, if you've done enough of these type of questions, then you'll understand that cot is 1/10. Okay, and then I can just make that equal to x because um, I'm just rearranging 2/14. And if I think back to my original question where I have the complex number w equals x plus I, then I know my I component is positive because I have a plus I. So if I think of my Cartesian plane, which quadrant am I talking about in terms of angles for this w? It would have to be either first or second quadrant, and it would be in my first quadrant because I have a positive x. So these are my positive x values. And then I have a positive y value as well. And remember again, I reiterate, x is my real component, and it's also the cos aspect, and then my y component is my imaginary, and it's my sine component, okay? And it has to be on the first quadrant, so I need to be, basically, when I determine all the possible values of x, I need to be thinking in my, thinking about just the first quadrant, angles, okay? So I'd say as w equals x plus I, then x is any positive real value, and um, I guess my imaginary is positive, real positive as well. Then I need to consider my 2n plus 1 times pi over 14 for angles that lie in quadrant 1. Okay. And then I can start off by doing n equals 0, again, as I said, and that would give me 2 times 0 plus 1 is 1, so that's pi. X equals cot pi over 14, right? And I know that pi over 14 is that going to be in my first quadrant, so I know my boundaries is going to be an angle from 0 degrees to pi over 2 degrees, okay? Or radians in a way. It's the unit, and then I just keep going my positive integers because I've made my n a subset of integers. So I'll do n equals 1, and that in that case my x is equal to cot 2 times 1 plus 1 is 3 pi over 14. Okay, and I know that in terms of 14, half of 14 is 7, so I need to keep going until I reach 7 pi over 14 essentially. And I technically can't do 7 pi over 14 because that means my x component will be 0. So I can't go up to there. So n equals 2, x equals cot 2 times 2 plus 1 is 5 pi over 14. Okay, and those are my values for x, because if I do n equals 3, in my head, I'm thinking 3 times 2 is 6 plus 1 is 7. 7 pi over 14, that's pi over 2. So I'm already on the y-axis. But because simply just my y value, sorry, my w value has an x and a y component, or imaginary and real component, I need to be sitting within the first quadrant, not on the line, because that means I would have an, if I was pi over 2, then that means that my x component would be 0. Okay, the x component is 0 for w to the power of 7, but not for x itself. So I need to consider that. So just wrapping up now, for the marks, I got the first mark by using de Moivre's theorem correctly, and then correctly determining an expression representing the argument of w in terms of x. So that is this one here. And then determining a relationship now of the argument for w to the power of 7 is this one. And then a general expression for x. And then, interestingly, you get a single mark for determining one value of x, so you still get part marks if you don't understand about all this domain stuff, making sure it's in the fourth quadrant, but that last value is really evaluating the reasonableness of solution by determining the remaining 2 values of x. So basically you need to have 3 possible values of x to get full marks, and those last 2 marks particularly.